growing from ancient astronomical observations 2,500 years ago to black holes in space. No human endeavor has transformed society and defined our place in the cosmos more than the physical sciences. What started as a kernel of knowledge about the movement of the heavenly bodies has expanded to include the atomic building blocks of all chemistry. Geology's understanding of Earth's long history and the forces that have shaped our planet's features. Astronomy's picture of an ever-expanding universe populated by billions of galaxies, each containing billions of stars. And physics' understanding of the basic principles of movement, energy, and forces which have given us the technological world of cars, planes, television, computers, cell phones, and the electrification of the planet. Turning Points in the Physical Sciences takes you on an exciting journey of discovery from ancient through classical science to the world of modern physics, relativity, chaos theory, and quantum mechanics. By the mid-19th century, the visible solar system was well known to anyone interested in astronomy. From the Earth's perspective, there were 2 inner planets and 4 outer planets. Uranus, the most distant, was just barely visible to the naked eye. Further, as Copernicus and Kepler suspected, the hole in the solar system between the orbits of Jupiter and Mars was now filled with a new kind of celestial body, the asteroid. Small fragments of either a former planet or the failed attempt to form a planet. Indeed, in 1807, the first asteroid was discovered by Giuseppe Piazzi while compiling his comprehensive catalog of stars. At the same time, astronomers noted that Uranus was behaving unusually, accelerating and then decelerating as it traversed the night sky. Many suspected that only a new planet outside of Uranus could produce such a result, but how to find it? Using calculus and the laws of motion, a Cambridge mathematician, John Adams, predicted the location of a new planet in 1845, as did Leverrier working at the Paris Observatory. A race was on, a race that was won by the French when Johann Gottfried Galle, who, working at the Berlin Observatory, became on September 23, 1846, the first to look at Neptune, the 8th planet in the solar system, and know it. He had used Leverrier's calculations. The search for Neptune ushered in a new era in astronomy. Earlier, observations had demanded explanations, but from now on, the theoretical models would predict phenomena, such as the bending of light by the sun during an eclipse. And observational astronomy would play the role of substantiating or refuting theory. Aided by the powerful tool of celestial photography, the 9th planet was discovered at Lowell Observatory on February 18, 1930, by Clyde Tombaugh, called Pluto. It was unlike the other planets. Instead, it was made up of rock and ice. By the turn of the millennium, other Pluto-type planets were suspected to exist on the edge of the solar system. Albert Einstein said, "Maxwell's change in the conception of reality is the most profound and most fruitful that physics has experienced since the time of Newton." Up until Faraday demonstrated electromagnetic induction in 1831, forces were thought of as central, such as when a racket impacts a tennis ball. However, in electromagnetic induction, a current that is started and stopped in the first coil is detected simultaneously in the second coil without any physical connection. Faraday explained this result not by evoking a central force, but by lines of force, that is, a field. No one recognized the tremendous significance of Faraday's explanation except the shy Scottish physicist named James Maxwell. In a stroke of genius, Maxwell saw that electricity, magnetism, and light were all interconnected. In fact, he stated light was made up of electricity and magnetism. It was electromagnetic radiation, and it traveled in waves at the speed of light. In this animation, a wave is produced when an electrical field, shown by red arrows, and a magnetic field, shown by blue arrows, combine to produce a wave. Maxwell precisely expressed his ideas mathematically in a series of papers that culminated in 1864 with his now famous four equations. Improbable as it may seem, if Maxwell's new model of reality was true, scientists would have to accept that the world was made up not of objects, as ordinary senses suggested, but of overlapping fields. Because of this conceptual challenge and the fact that his mathematical equations were impossible for most to understand, it would take a generation to grasp the full impact of Maxwell's leap of thought. Further, Maxwell predicted that there should be other electromagnetic radiation on either side of the visible light spectrum, and indeed there was. We're all familiar with waves on the ocean. The rise to a high called the crest, and fall to low, the trough. The wavelength is the distance measured from one crest to the next. For example, light waves are about the size of a microscopic animal or cell. Could there be larger electromagnetic waves, and what would they be like? Over 20 years after Maxwell's papers, a German physicist, Heinrich Hertz, built this setup. When the rods on the device on the right were given opposite electrical charges, a spark was produced in the gap. Like in this simple radio transmitter, Hertz oscillated the charge back and forth. In the process, electromagnetic waves detached and were picked up without a physical connection by the second device, producing an electronic current lighting up a bulb. The waves produced would eventually be called radio waves. Hertz went on to show that radio waves had all the properties of light, even though we could not see them. They traveled at the speed of light. They could be bounced, refracted, polarized, and they were of a length that varied from the size of the human to a tall building. When asked what could be done with the man-made electromagnetic waves, Hertz replied, "Nothing, I guess." He could not have been more wrong. In 1901, Marconi ushered in the wireless age when he transmitted the first point-to-point radio signal from England to Newfoundland. 100 years later, radios, televisions, and cellular phones are as commonplace as horseshoes were in Hertz's era. As for Maxwell's equations, understanding their full importance had just begun. By the mid-19th century, the number of identifiable elements had grown to over 50, enough to stock a chemistry lab and enough to look for ways to organize them. At that time, it was known that each element had the possibility to exist in 3 states: a gaseous state, such as oxygen and hydrogen, a liquid state, such as mercury, or solids, such as copper. But was there any other order to them? In 1869, Russian chemist Dmitry Ivanovich Mendeleev made a startling discovery. He wrote the symbols for the 65 known elements on cards with their atomic weights. On a cold winter night, he shuffled them around, finally putting them in columns and rows showing similar chemical properties. What he found was an underlying pattern, a repetition of properties. Mendeleev discovered what is now called the periodic table of elements. However, his table had gaps. Mendeleev was so confident in his discovery that he not only predicted these missing elements would be found, but also what their properties would be. Time proved him correct. In the decades since he developed his periodic table of the elements, scientists around the world raced to be the first to discover new elements and fill in his chart. There are now 9 basic element groups: alkali metals, alkaline earth metals, transition metals, other metals, metalloids, nonmetals, halogens, noble gases, and rare earth elements. To see commonalities within each group, take the nonmetal group, for example, which contains some of the most important elements for life: hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, selenium. This piece of coal, carbon, is typical of the group. It is brittle and cannot be made into a wire. In fact, all the elements in this group cannot conduct electricity, and they do not reflect light like a metal does. On the other hand, the transition metals form a large group of elements. Using copper as an example, they are all ductile and malleable. They all conduct electricity and heat. Interestingly, the group also contains the only elements that produce a magnetic field: iron, cobalt, and nickel. Finally, the noble gases. Typified by neon, which lights the urban night, are all highly stable, rarely interacting with other elements. Understanding why there is this periodicity of elements would have to wait until the quantum mechanics solar system model of the atom was revealed at the beginning of the 20th century. However, by the 21st century, the number of elements had grown to over 110, with over 20 now being man-made at such high-tech facilities as Argonne Laboratory, Fermilab, Lawrence Livermore Laboratory, and Thomas Jefferson National Accelerator Facility. As for the periodic table, it has expanded and been revised a number of times, but Mendeleev's original pattern is still there, embedded in each new edition. By the last decade of the 19th century, scientists were feeling confident about their understanding of Maxwell's electromagnetic spectrum. Electromagnetic waves of various lengths or frequencies that traveled at the speed of light. On the long end of the spectrum were radio waves that were used to transmit sound from point to point. Microwaves, used today in cooking with microwave ovens. And infrared waves, waves that were originally discovered in 1800 by Herschel when he measured the temperature of the colors split by a prism and found that the highest temperature was an area of invisible light next to the red wavelength. They also knew that visible light formed the smallest group of frequencies. It was followed by the ultraviolet light frequencies that tan our skins and cause various chemicals to fluoresce. Then 2 discoveries shook late 19th century scientists out of their complacency. On November 8, 1895, a German physicist, William Röntgen, was experimenting with a cathode ray tube, a kind of vacuum tube, and the basis of every television and computer screen today. These tubes worked by having a negative and positive terminal inside an evacuated glass container, so that when a high voltage current was passed through the tube, a beam was produced called a cathode ray. Like many others at the time, Röntgen was investigating the nature and properties of this curious beam, one of which was that the range of a cathode ray was short, just a few inches. So it was with some surprise that he saw a phosphorescent material on the other side of the room light up when the beam was initiated, especially since his tube was encased in cardboard. A few days later, in what must have been a wonder, Röntgen held his hand between the tube and the screen and saw his bones. Then on the 22nd of December, he made the first radiograph of his wife's hand, wedding ring and all. Röntgen had discovered a new, short, high-frequency form of electromagnetic radiation. He had discovered X-rays, and a way to look inside the body of an animal. At the time, X-rays appeared to many like black magic, but over the next century, X-rays would prove invaluable in medicine and in unlocking the secrets of crystal structures. The next year, 1896, would bring an equally surprising discovery. French physicist Antoine-Henri Becquerel believed that X-rays were produced by phosphorescent compounds, and he set about to test his theory. Becquerel took phosphorescent compounds, placed them on a photographic plate wrapped in black paper, and set them in the sun. Knowing that the X-rays would pass through the paper, he hoped to see their telltale signatures when the plates were processed. Moving from specimen to specimen, his next sample was uranium-potassium sulfate, but the day was cloudy, so he simply stored it with a photographic plate in a drawer for a number of days. Then, for some curious reason, he processed that photographic plate, and to his surprise, the plate was exposed. Somehow, the uranium was giving off a new kind of penetrating ray. Building on Becquerel's results, Polish chemist Marie Curie found that this property, which she called radioactivity, was common to uranium and thorium, two naturally occurring elements. Curie also found that the kind of rock called pitchblende was even more radioactive. Immediately, she and her husband went to work refining tons of pitchblende ore, and in 1898 announced to the world the discovery of two new radioactive elements, polonium and radium. Radium was so radioactive, it was used to light up watch dials in the dark. In fact, it is the most radioactive of all naturally occurring elements. Later, physicists would determine there are three forms of radioactivity: alpha particles, beta rays, which are actually particles, and gamma rays, the highest energy wave on the electromagnetic spectrum. Unfortunately, Marie Curie and her husband received lethal doses of radiation during their work. Radioactivity proved to be both a tremendous servant for mankind's benefit and a dangerous element for its destruction. At the end of the 19th century, two debates raged in the world of physics. Did atoms have parts? And what was the nature of the beam inside a cathode ray tube? In 1897, Cambridge physicist J.J. Thomson astonished the scientific community with experiments that answered both of these questions. Thomson hypothesized that cathode rays were made up of small pieces of the atom. He had found that the cathode rays travel much slower than light, and that they were negatively charged, since they were bent by the negative end of a magnet. Further, the particles emitted by the positively charged electrode of the cathode ray tube were the same, no matter what kind of metal was used. There was no difference between a copper-produced ray and an aluminum-produced ray. Consequently, Thomson announced to the world on April 30th, 1897, that cathode rays were negatively charged particles, many times smaller than an atom. He called them corpuscles, a term that would quickly be replaced by electron. Electrons, Thomson concluded, were part of all matter and the universal carriers of electricity. But physicists knew there had to be something more to the atom, since atoms that make up copper, for example, were neutral in their charge. A positive force must be balancing the negatively charged electrons. At first, a model of the atom arose that had electrons embedded in a positive mass of matter, much like raisins in a pudding. However, in 1911, Ernest Rutherford bombarded gold foil with alpha particles, positively charged particles that were one of the products of radioactivity. Most of the alpha particles passed through with ease, but then one bounced straight back. It had been repelled by the positive core of the atom. Rutherford was forced to conclude that atoms were composed mostly of empty space, that an atom was made up of a positively charged nucleus with electrons orbiting around it. 20 years later, English physicist James Chadwick completed the model of the atom with the discovery of a third fundamental particle, the neutron. A particle slightly larger than a proton, found in the nucleus, but with a neutral charge. The solar system picture of the atom has withstood the test of time, but it would take physicists decades to explain how it worked. As the 20th century dawned, scientists believed that the study of physics and chemistry was nearly completed. All that remained was to tidy up some loose ends. The science that emerged from the previous century had given a wondrous technology to the world. The electrification of cities and homes, telegraph, telephones, radios, TVs, automobiles, and powered flight. It was a time of great triumph for what would become known as classical physics and chemistry. The new inventions and technology it spawned grew and accelerated into the 21st century. Newton's laws of motion had replaced a God-directed universe. The new paradigm was the clockwork universe. Know the state of the universe at any given moment, and the complete past and future could be calculated. What was real, always the proper subject of science, were a few basic types of particles, the parts of atoms, and the void. The space particles traveled in. The perplexing problem of action at a distance, for example, the attraction and repulsion of two magnets, had been explained by the addition of fields to the fundamental concepts of physics. A moon revolves around Jupiter, not because it feels the distant presence of Jupiter, but because the moon entered Jupiter's gravitational field. A field is just there, pure potential until something enters the field. So the world of classical science was made up of particles and fields that operated according to Newton's laws of motion and Maxwell's electromagnetic field equations. Only a few problems remained. One was the black body problem. As most people know, a piece of metal in a dark room is a black body. At room temperature, it emits no radiation in the visible range of the electromagnetic spectrum. But when metal is heated, it begins to glow, and as more heat is applied, it goes from red to white hot. Maxwell's equations implied that it would take an infinite amount of energy to make this happen. However, this wasn't true. On December 14, 1900, Max Planck, a German physicist teaching in Berlin, presented a solution to the black body problem. What he did was assume that light was being emitted in chunks, or discrete packets, of energy. He called these chunks photons or quanta. In one fell swoop, the foundations of classical science were about to be shattered. A new paradigm of reality was about to emerge, one that would encompass relativity and quantum theory. Most people in the 21st century still have not accepted or understood the deepest and most profound implications of this new paradigm. such as there are no independently existing objects as we once thought electrons, protons, and neutrons were. From now on, physicists would have two areas of exploration: the continual development of classical physics and its ever-expanding new technologies, and modern physics with its own technological implications.